Welcome back to Stellar Pulsations. We started this morning with a digression on stellar evolution, and I promised you to cover some selected problems of stellar evolution, which are, so to say, or in a certain sense, also connected to stellar pulsations. Stellar evolution and the construction of stellar models is a prerequisite of the study of stellar pulsations. So we should know a little bit how stellar evolution proceeds, what are the main outcomes of stellar evolution, and how do we construct stellar models. Okay, there are several topics. The first one is stellar parameters. Okay, so let's turn to the apparent stellar parameters. The chemical composition observed to construct the stellar model. In particular, our equation of state and the nuclear energy generation rates and the opacities, they will depend sensitively on the chemical composition. So we have to know how many hydrogen, how many helium, and how many of the heavy elements are within the mixture which mass of the sun. Some stars are much less massive and some stars are more massive than our sun. Then what we observe is the brightness of the star, and for a theoretician, it's not the brightness of the star which we would like to use as a parameter, but we would like to use the counterpart of the absolute magnitude of the star, which in a theoretical sense is its luminosity, the energy per time our star emits over the entire spectrum. So this is the complete energy output of the star in terms of energy per second in all integrated, so to say, over all. We know there are blue stars and red stars, and the difference between them is their effective temperature. In defining the effective temperature, we've already made use of a relation between the parameters of the star that a zeroth approximation to any star and its radiation is that a star radiates as a black body. If a star is considered to first or zeroth approximation as a black body, then the flux per, it means the energy per area and second emitted from the star, will be effective temperature is defined by assuming that the star radiates as a black body, and the position in the star where the temperature is equal to this black body temperature is called the photosphere. So the photosphere, the star has a temperature which is equal to effective temperature, and the effective temperature is gained by, if we transfer it from flux to the luminosity, then the luminosity is the area of the star, or the area of the photosphere, times the flux. This means that the luminosity then should be proportional to the sphere, to the surface of the photosphere, which is its radius squared, proportional to its radius squared. And therefore, the luminosity has to be proportional to radius squared times the effective temperature to the power 4. A convenient representation of, say, luminosity and effective temperature, maybe you who has done some astronomy will know it, is the Hertzsprung-Russell diagram, where the observer plot the magnitude, sometimes the apparent magnitude, it's better to put the absolute magnitude against the spectral type or the effective temperature. For historical reasons, the hot stars are on the left-hand side of the diagram and the cool stars are on the right-hand side. So we can introduce in this diagram lines of constant radius. Maybe this is known to many of you, most of you. Well, luminosity, theoretician would take the luminosity and the would take the effective temperature, where the effective temperature goes that way. The high effective temperatures are on the left-hand side. And actually, it's usually a log diagram, so log L against log T effective, and we have the Stefan Boltzmann's law valid in this diagram. So this is the usual way representing at least these two parameters together with radius in the Hertzsprung-Russell diagram. The mass, of course, is not so easy to display, and it's one of the parameters which are very difficult to determine. Usually the mass is known not to the same degree as luminosity and effective temperature. In this diagram, you can plot the lines of constant radius. So we have luminosity is proportional to r squared times the effective temperature to the fourth. So in a log-log diagram, lines of constant radius would be lines where log L goes to, log L is 4 times log T effective. Because we take it the opposite way, it's lines of slope minus 4. So these are curves of constant radii. These have slope minus 4, and the small radii are on the left bottom corner, and the big stars are on the right upper corner. So these are the dwarfs, small stars, and there are the giants on the other side. So this is how these two parameters are displayed. The mass, it's not that easy, but the Hertzsprung-Russell diagram is one way to represent stellar parameters. Well, there is actually a maximum to the luminosity, and we will see why. Let's consider the equation of radiative transport. Luminosity is proportional to the temperature gradient here in the Lagrangian scheme. Luminosity is minus diffusion coefficient times the temperature gradient in terms of mass. So taking the Lagrangian variable mr as the independent variable. Now I pointed already out that this factor t to 3 can be rewritten in terms of either the radiation energy density or the radiation pressure. Radiation pressure is given by P rad. P rad is proportional or is equal to a third times temperature to the fourth. So the a third times temperature cubed times the temperature gradient might be written in terms of the gradient of the radiation pressure. Even we can also take out one density, and we can transform from the mass as a Lagrangian variable to the radius as an Eulerian variable. Then we get a factor of 1 over 4 pi r squared rho, and we can rewrite this equation for radiation transport like the luminosity is given by this factor, which contains as an important quantity these r squared and the opacity. Well, a gradient of a pressure is nothing else but a force per volume. Pressure is force per area. So this is force per volume, and we can get an acceleration from that simply by multiplying it by 1 over the density. So 1 over the density times the gradient of the radiation pressure is something which is the acceleration caused, or the acceleration exerted on matter by the radiation pressure. So 1 over rho gradient of radiation pressure is the acceleration of matter coming from the radiation. So the radiative acceleration, A rad, is simply minus 1 over rho times the gradient of radiation pressure. And we read off from this equation that it's given by kappa over 4 pi c r squared times the luminosity. Now, there is not only the gradient of radiation pressure, which needs to balance gravity in an equilibrium situation. The total pressure gradient balances gravity. The total pressure gradient contains not only the radiation pressure gradient, but also the gradient of gas pressure. So for equilibrium, we need that the radiation pressure, that the radiative acceleration should be smaller than the gravity. If radiation pressure is already bigger than gravity, then in addition, the contribution from the gas pressure gradient will always exceed the gravity, so the maximum radiation pressure is gained once we have that the radiative acceleration is equal to gravity. This is the maximum which we can have, otherwise we will not find an equilibrium. Okay, agree? For equilibrium, we need that this radiative acceleration should be smaller than the acceleration by gravity, which is given by gm over r squared. But keep in mind, we have an additional acceleration by gas pressure gradient, so the maximum is really given once the radiative acceleration is small, it has to be smaller than the gravity. So if we insert this now here for radiative acceleration and the gravity, well, both scale with 1 over r squared, so the 1 over r squared cancels, and we are left with a condition from here that the luminosity has to be smaller than some constants involving speed of light, gravitational constant, and the mass divided by the opacity. So two factors matter for this maximum luminosity. It's the mass and it is the opacity. This luminosity, which is given by this expression, is called the Eddington luminosity, which is the maximum luminosity of any object that is kept in equilibrium by gravity. So they cannot have a bigger luminosity than this value, otherwise the radiative acceleration would become bigger than the gravity, and there is no equilibrium possible anymore. We are talking about equilibrium. Sometimes people confuse it with stability. We have nothing said about stability. It's a condition for the existence of an equilibrium. So if we don't match this condition, we cannot even have a stationary or a configuration in equilibrium, irrespective of the stability or instability of the object. So this is not a stability criterion, it's a condition for the existence of an equilibrium at all. Okay, so Eddington luminosity is the maximum luminosity for some equilibrium or static configuration with mass m. How big is it? The question, so we just have to insert this a typical value for the opacity and the mass for the sun, for instance, then on scale or express the mass in units of the solar mass. Then we have L Eddington, the Eddington luminosity is around 10 to 4 solar luminosities times the mass over the mass of the sun. So there is an important limit for the luminosity, which is the Eddington luminosity. Actually, once we consider pulsating stars, some of them are pretty close to the Eddington limit, so they are still in equilibrium, but they might be stable or unstable. Stability is a completely different concept from equilibrium. For stability, we have to have first an object which might be unstable or stable, which has to be in equilibrium. So the first condition would be we have an object below the Eddington limit where we can construct a stationary equilibrium configuration, and then afterwards we may ask the question, is this object stable or not? So don't confuse the concept of equilibrium, existence of equilibrium, with the concept of stability or instability. Okay, that's what I wanted to say about the stellar parameters. Well, the next issue would be the equation of state. Okay, this is an important point or an important quantity, an important issue to close the system of our equations. Well, stellar matter, that's taken from the observations. If we observe a star, we observe that it has a chemical composition. We can deduce it from the spectral lines we observe. So we see that stellar matters, once we look at the spectrum, contains a mixture of various nuclei, atoms, ionized atoms, electrons, and of course, because we see the star, a lot of radiation. The temperatures and densities which we deduce from the observations, the sun, for instance, has a photospheric temperature of around 5000 K. The temperature will increase inside because pressure and gravity should be in equilibrium, and therefore the pressure must increase inward, and therefore also the temperature. So the photospheric temperatures are the minimum temperatures. The temperatures will increase towards the center. And if we compare then, if we look at the densities, the mean density of the sun is remarkably low. Does anybody know what is the mean density, roughly order of magnitude of the sun? Yes, it's close to 1 gram per cubic centimeter. So it's pretty low density. And if you consider temperatures and densities gained from observations, then you would say, or you would conclude that it's the stellar matter has the aggregate state of a gas. It can be described by the equation of state of a gas in the ideal case, or in the case when the densities are very low and temperatures are high enough. That means we can describe the particles, the atoms, nuclei, ionized atoms and electrons simply by an ideal gas. And the equation of an ideal gas is given by gas pressure is proportional to the temperature and is proportional to the density of the star. And to account for the chemical composition, we have here the mean molecular weight. And the mean molecular weight should include the chemical composition, different chemical composition, but it also includes the physics of ionization. So the mu has to be determined in a very complicated way by considering the ionization states of different atoms, whether we have ionization, to which degree. It has to include the various energy levels within an atom. So it's a rather complicated way to determine the mean molecular weight, taking into account all the ionization processes, and this mu itself depends on chemical composition, depends on the density, depends on the temperature, and it requires a lot of atomic physics and atomic calculations to get out the mu as a function of density and temperature. So keep in mind, well, it's not that simple in the outer layers of the star where we have ionization processes, incomplete ionizations in the star. This mu depends sensitively on temperature and density and on the chemical composition. So mu itself is a function of rho and T. Okay, and then this is a description of matter within our star and the description of radiation, the pressure of radiation. It's much simpler. Radiation pressure depends only on the temperature, and we already wrote it down. Radiation pressure is radiation constant over 3 times temperature to the 4. So for normal stellar matter, for ordinary stellar model, the total pressure, the equation of state for the matter is given by the sum of gas pressure plus radiation pressure. It's usually written down in the form gas constant over mean molecular weight times density times temperature. That's the gas pressure plus radiation pressure. This is A over 3 times T to the 4th. Once we have the pressure as a function of density and temperature, or you can also take pressure as a function of density and entropy, or temperature and entropy, we also have a caloric equation of state, which tells you the dependence of the specific internal energy on temperature and density. Well, the specific internal energy for the gas is 3/2. This comes from the 3 degrees of freedom. Each degree of freedom gives you 1/2 kT. So this is the 3 translational degrees of freedom. 3/2 R over mu. If you compare it to the pressure, it's a very, very similar relation. So pressure is R over mu rho T. So this is 3/2 R over mu times T. And for the radiation pressure, we have that the energy density goes with A times T to the 4th over rho, because we have the specific internal energy U here, plus, of course, any energy density is only determined up to a constant. So these are the 2 equations of state we usually have for the matter: the thermal equation of state and the caloric equation of state. Once we have these 2, then we can play around with the thermodynamics, and we can derive from these 2 any other quantity we want to determine, which is, for instance, the entropy. If we have pressure and internal energy, we can calculate the specific entropy. We can calculate some of the coefficients which we need for stellar evolution, which is the specific heat at constant pressure. These are the coefficients, the logarithmic derivatives occurring as coefficients in the equation of state. So this is d log rho by d log P at constant temperature, and this is d log rho by d log T at constant pressure with a minus sign. We also have quantities like this, nabla adiabatic. This is defined as d log P by d log T at constant entropy. This definition of nabla adiabatic, this is determined by the equation of state. Without any reference to a particular stellar model, nabla adiabatic is simply a quantity to be determined from thermodynamics of the matter. So this can be deduced directly by means of standard thermodynamic relations. Okay, I wanted to say something else. Okay, I forgot. Well, this equation of state is valid as long as the temperature is high, or comparatively high, and the densities are low. Okay, so what happens if we go to low temperature, and the question is then whether these conditions appear also or are also present in a star. What happens if temperatures are moderate, or for terrestrial standards it might be even high, but if the density becomes high? Well, for this purpose, let's consider the pressure of electrons. Let's consider the situation that the stellar matter is completely ionized and that the electrons contribute significantly to the gas pressure in that sense. So they make up a significant contribution to the pressure. What happens to them at low temperatures? Well, if the temperature for an electron becomes low enough, then we have to take into account that electrons need to be described by Fermi-Dirac statistics. That means they are quantum mechanical particles with half integer spin. So electrons have half integer spin, and they are therefore fermions. They are not bosons, are those particles which have integer spins. So electrons are fermions which have half integer spins, with the consequence that in a quantum mechanical state we can get only two electrons, one with spin up and one with spin down. Or in other words, they have to be different in at least one quantum number. The quantum number would then be the spin. So, okay, so if we construct the possible states, the possible quantum mechanical states for the electrons, we can put into one state at maximum two electrons, spin up, spin down. Well, what is the potential in which our electrons move? Well, our star acts as a box. The electrons are contained in a box, and the box is provided by our star, a box or a potential pot. So the zeroth approximation would be we have a potential pot with infinite potential on the walls and zero potential in the middle. So we have to fill into our potential, we have to fill in our electrons. So for this potential pot, we have a fundamental state, a state with lowest energy, which is not zero. That's a quantum mechanical effect. There is the lowest energy state, and then we have a sequence of state. And once the temperature is low enough, then all these states are filled up to a maximum energy. If the temperature is high enough, of course, they can escape here and can take other states or can become unbound to the system. But if the temperature is low enough, then they have to be filled in the potential pot of our star and have consecutively fill all these states up to a maximum energy. When we have put in all electrons, then we arrive at a maximum energy E0, or equivalently at a momentum P0. Energy E0 corresponds to the maximum momentum. Okay, that has to be done once we go to very low temperature. We have to take into account that these are fermions and they have to obey Fermi-Dirac statistics. Okay, for T going to zero, all states are occupied up to maximum energy corresponding to maximum momentum P0. And this effect is known as, or is called, degeneracy. So the electron gas becomes degenerate, and this means it fills all possible states, all the available states, up to a maximum energy and a maximum momentum, which depends on the number of electrons we have to fit in. So if the maximum energy is defined by the number of electrons which we have to put in our potential pot. Okay, what does it mean? Well, number density is, well, now we would like to take this picture and we would like to know the number density, or the relation between the number density, the maximum energy, or the maximum momentum of our electron distribution. Well, the numbers of electrons will be proportional to the space available to the phase space available to the electrons. This is nothing but the number of states here we have in energy to fill. Well, this will be proportional to the phase space in energy or to the phase space in momentum. So it's simply proportional to the volume of phase space which are accessible to our electrons. The number density of electrons will be the integral over the phase space. This is the phase space volume in spherical coordinates. So we take the phase space in 3 dimensions and take a spherical distribution. There is no position in phase space is special. So there is it's simply the volume of phase space integrated from 0 to the maximum momentum. Well, this integral is easily calculated. This goes with P naught cubed. So the number of electrons per volume which we can fit in is proportional to the maximum momentum of the distribution in our potential pot. The energy density then is simply given by writing the energy per particle here and also integrating over the momentum or the phase space. So the energy density of our particles is the integral over the phase space times the energy of a single particle, also taken from 0 to the maximum momentum. Okay? Well, now we have to distinguish between between the properties of the particles and the relation between the energy and the momentum of the particle. If the particle is a classical particle, a non-relativistic particle, then we have that epsilon is the kinetic energy of a particle is given by the momentum squared over 2m. Is this known to everybody? The kinetic energy is given by momentum squared over 2m. So we have to insert this here, but that's not always true. For very fast particles, which are relativistic, the epsilon is a linear epsilon, and the momentum is a linear relation. Then epsilon is given by speed of light times the momentum, and in that case, we have a different relation between the energy and the momentum. So this integral will be different once we consider non-relativistic or relativistic particles. So the energy density goes with integral over p to the 4th for the non-relativistic particles, or goes with p to the integral over p to 3 for the relativistic particles, and that means that the energy density goes with the maximum momentum to the power 5 for non-relativistic particles, and goes with the power with the maximum momentum to the 4th power for the relativistic particles. Okay, now we have 3 relations. We have that the number density goes with maximum momentum to the 3rd power. The energy density goes either with a power 5 or power 4, depending on whether our particles are relativistic or non-relativistic. And now we can construct from that a relation between the electron pressure and the density in the following way. The electron pressure is proportional to the energy density with a factor 2/3 for non-relativistic particles and with a factor 1/3 for relativistic particles. Actually, in the following, these 2 factors will not matter. It's the dependence on the maximum momentum which will matter in a second. So this goes, pressure of the electron goes with the maximum momentum to the 5th power, non-relativistic case, and with the 4th power in the relativistic case. Now we know that the maximum momentum is related to the number density of particles. Number density goes with the third power of the maximum momentum. So we express the maximum momentum in terms of the energy density. Maximum momentum goes with the 1/3 power of the number density. So we have, in the end, that the pressure goes with the number density of the electrons to 5/3 in non-relativistic case, and with the power 4/3 in the relativistic case. If we have charge neutrality, then the number density of the electron will be proportional to the mass density of the nucleons. So this will be then of the order of the number density of the electron will be proportional to the density, and the same also for the relativistic case. So we have that the electron pressure will go with the density to 5/3 non-relativistic, and will go with the power of the density to 4/3 in the relativistic case. What we see here, it's obvious, of course, from the construction, the temperature does not enter this relation. So we have an equation of state relating pressure and density only. Temperature has been dropped. Temperature is no longer a parameter, and this is another expression of degeneracy. Yes.
How we got that 2/3 and 1/3 factor?
Well, I haven't proven that. This is a general relation. If you are interested, I would ask you to go to thermodynamics, where the relation between pressure and energy density is calculated for relativistic and non-relativistic particles. Anyway, this fact, it's given just for completeness. These factors do not matter for our purposes. I have edited just for completeness. I'm sorry, I didn't go into further. Otherwise, I would have to present a complete lecture on thermodynamics. I'm sorry about it. But it doesn't matter. If I would have left it, you get the same result. Okay. Well, let's go further on. Well, the question is, what is the condition for temperature to be small? Well, temperature to be small, we have said, well, for low temperatures, this means we have to specify what we mean by low temperature. It means that the thermal energy, the usual thermal energy of an ideal gas, where the thermal energy of a particle is of the order kT. If this is small compared to the maximum energy once we have complete degeneracy, then we say the condition of degeneracy is satisfied. So in order to see the effect of degeneracy, this means that the maximum energy in the degenerate case of degeneracy, it has to be much smaller, much bigger than the thermal energy. This is the condition for degeneracy. Well, and taking the case that the particles are described by classical particles, non-relativistic particles, this maximum energy is related to the maximum momentum by p0 squared over 2m, and m is the mass of the particle. Now, if we insert again the relation between maximum momentum and the number density, so kT has to be smaller than 1 over m, the mass of the particle, times the density of our electrons to 2/3. This relation actually is valid for all fermions. And so what you see or deduce from this relation here is that the onset, or that the degeneracy comes later for more massive particles. The degeneracy condition is satisfied for more massive particles later than for the small, less massive particles. So the particles, the lightest particles we have in our stellar mixture are the electrons. So the first ones who will degenerate are the electrons, and the nuclei still are non-degenerate because they are at least 1,000 times more massive than the electrons. So we have in our mixture, once the degeneracy sets in, degenerate electrons and non-degenerate thermal nuclei. That's why we have to deal with the degeneracy of electrons first. The degeneracy of nuclei comes much later. Okay, the nuclei degenerate later than the electrons at lower T, and in the degenerate situation, the degeneracy pressure will always be much bigger than the thermal pressure. So in that case, once we have a mixture of non-degenerate and degenerate particles, always the degenerate particles will be responsible for the pressure and the other particles will become negligible. So the nuclei will be negligible concerning the pressure compared to the electron pressure once the electrons degenerate, once the electrons becomes degenerate. So for degeneracy, electrons, yeah.
Working in the units C equal to 1 and Z equal to 1.
Natural.
Pardon? C equals G equal, no. I have dropped all the constants here. It's just the relation. Well, all constants have been dropped. Only those quantities which are interesting have been kept. So that, of course, you have to, in order to get the dimensions right, you have to add some of the constants C and whatever. For clarification, I only took those quantities which are important physically. Okay. Another consequence of that is once we want to keep the degree of degeneracy, well, we can take this ratio, temperature to the density to 2/3 constant. We can take the ratio of kT and the P naught squared over 2m as an indication for degeneracy or as a degree of degeneracy. Once we would like to keep this ratio of thermal energy and degeneracy energy constant, then we see here that then the temperature would have to go with the density to 2/3. Only then we have a constant degree of degeneracy. So if we want to keep the degeneracy constant, this will become more important later. Then the temperature has to increase with the density, at least with a temperature with a density to 2/3. If it decrease more with a lower exponent, then the degree of degeneracy will increase. If the exponent is bigger, then it leaves the degeneracy and becomes less degenerate. Okay, well, again, to summarize, degeneracy means the equation of state becomes independent of the temperature. So if the temperature is low enough, then we have that the pressure is equal to the electron pressure. The electron pressure then only depends on density, and therefore the pressure only depends on density because the pressure of the non-degenerate particles becomes unimportant. And we have to distinguish between non-relativistic electrons and relativistic electrons. For the non-relativistic electrons, we have pressure proportional to rho to 5/3, and for the relativistic ones, we have pressure proportional to the density to 4/3. By the way, how big is alpha and delta for these guys? D log rho by D, the alphas and deltas are defined by an equation of state of that form, rho of P and T. Well, the dependence on temperature is dropped. So what is delta here? D log delta was D log rho by D log T at constant pressure. It's 0, so delta is 0 for a degenerate gas, and alpha is equal to d log rho p, it's the inverse. So d log rho by d log p is 3/5, or it's 3/4 for the relativistic electrons. So this, you see, this is one case where you can apply this definition of alphas and delta. By the way, what is alpha and delta for an ideal gas? P is P equal to rho times T, or rho is P over T. Log rho is log P minus log T. So alpha and delta is unity. Alpha is equal to delta is equal to 1. Okay, just as a small by remark. Okay, well, the question is degeneracy such a remarkable effect which occurs only in strange astrophysical situations? I will promise you it occurs. Some stars are living from this degeneracy effect. Or do we observe degenerate electrons also on Earth? Do we see degenerate electrons on Earth? Well, think of everyday life. Is there someone who is familiar with solid state physics, with metals? Electron in metals are degenerate. They suffer from the same degeneracy as the electrons in a star at low temperatures. So degeneracy is nothing very uncommon. It happens in a metal. It's normal for metals. Okay, so I have now, unfortunately, it's a diagram in German. Well, the various domains where the different equations of states are valid is given here in a temperature density diagram. So we have log rho here, the density we have as a function of log rho and log t, the various ranges where the various equation of state are valid. So at very low densities, very high temperatures, we have radiation pressure. So low temperatures, low densities, and high temperatures mean we have a normal, so-called normal equation of state, and low densities means the gas pressure becomes unimportant. High temperature, the temperature to the four terms will dominate. So this is radiation pressure. If we decrease the temperature, increase the density a bit more, then we end up with an ideal gas. So then the radiation pressure is no longer dominant, but the gas pressure being proportional to rho times T will become important. Once we decrease temperature even more and increase the density, we enter the domain of degeneracy. First, the non-relativistic degeneracy with alpha equals 3/5, delta equals 0. And if we increase the density even more, then we enter the domain of relativistic degeneracy with delta equal to 0 and alpha equals to 3/4. Ideal gas, again, alpha and delta are equal 1. Okay, that's what I wanted to say about the equation of state, and we will see the consequences for stellar structure and evolution later on, because there are stars which are governed by an equation of state which is given by the degenerate electron gas, and they have special properties, and we will study them on the basis of what we saw for the equation of state. P going proportional to 5/3 and P going proportional to 4/3 in the case of relativistic or non-relativistic degeneracy. Any questions? about that? Well, this actually one would have to go through the entire quantum mechanics to do this really in detail. I try to pick the most important parts and the most important connections here without reference to the complete thermodynamics. So there are of course some gaps here which I have to leave, but otherwise this would be a lecture on itself. Okay. Okay, so next quantity which we need to consider is the opacity. Well, the opacity describes the interaction of photons with matter. Absorption, scattering, any re-emission of photons by atoms, this is all described by the opacity. So in general, the interaction of photons with matter is described by the opacity. There's one source of opacity which is always present, which is very simple to describe. This is the scattering of photons at electrons. So if we have an ionized material, then we have sufficient electrons available. This happens inside the star. Deep inside the star, everything is ionized. We have free electrons, and the photons collide with the electrons. This is particularly efficient because they are the less massive particles, and therefore the scattering of the interactions with the electrons is the most important process. Well, this is called Thomson scattering. Electron scattering is Thomson scattering of photons at electrons, and well, I don't derive this in detail. You have to you have to go to quantum mechanics, quantum electrodynamics, to derive the cross section of the interaction of a photon with an electron. The result is pretty simple. It has a constant cross section. It does not depend on density and temperature. It's simply constant, and it's given by elementary constants. So it depends on the elementary charge, on the mass of the electron, and on the speed of light. These are the only dependencies. So it's a constant given only by fundamental constants. So what you have then as the opacity, once this is the cross section, the opacity is then given by this constant cross sections times the number density of the electrons divided by the density. Number density of electrons in the case of a fully ionized gas is essentially constant. So the number density of the electrons over the density is then given by the mass fraction of the hydrogen only, which accounts for, well, usually we have in a symmetric nuclear metal, we have 1 neutron per proton. This is not true for hydrogen, and therefore the hydrogen mass fraction occurs here. But so the opacity depends a little bit on the hydrogen mass fraction. It's given by 0.2 centimeters squared per gram times 1 plus x, because the proton, of course, that disturbs the symmetry of nuclear matter. We have then more protons than neutrons, and therefore the mass fraction of hydrogen comes in here. So this assumes fully ionized matter. So this is one source of opacity, and it's simply a constant. Of course, once we don't have electrons, for instance, if the matter is cool and we have recombination and the electrons disappear, then this source of opacity goes away. Okay, the next is the free transitions. What is that? Free transition. This means that an electron passes a nucleus or passes an atom, but it does not get bound. It just travels along on a hyperbolic orbit. That means it goes from a free state of an atom to a free state afterwards. free transitions. More important and more important are the bound-free transitions. These are the ionization or recombination processes. So a photon hits an atom and it removes an electron from the atom, which comes into a free state. The opposite would be the recombination. These processes take out a lot of energy, and these contribute to the opacity in a very efficient way. These are the bound-free transitions. So photoionization, keep in mind, is one of the processes which contribute to the interaction of photons and matter and lead to a significant contribution to opacity. The next processes are the bound-bound transitions, which have for a long time been ignored or largely ignored. Now I've again problems with the okay, thanks. Bound transition. This is an interaction with photons of atoms where an electron is put to a higher state, but it is still bound. So you have various levels within your atom. You take out, for instance, at the inner shell, you take out an electron and it's put on a higher energy level, but it does not get photoionized. So this does not lead to an ionization of the atom, but it still gets the atom into a higher energy state. These are the bound transitions, and we will see an example for that later on. Then there is a process which is important for low temperatures in stars, which is the so-called H- opacity. It is the process that a hydrogen atom, a neutral hydrogen atom, catches an electron, provides or goes to an H- ion. This is an equilibrium reaction, so it can go both ways, but it consumes energy from the radiation field, and in this way it can contribute to the opacity. So this process also contributes to opacity, but it's significant only at very low temperatures. And of course, I have to, for completeness, I have to add here the conduction. If the electrons become degenerate, then the conduction is a process, or it contributes, heat conduction contributes to the energy transport, and this conduction is usually or is done by the electrons, because then they have the biggest mean free path, and then they contribute, in, so to say, to the opacity. You can include conduction formally in the opacity, and this is done if electrons become degenerate, but we will not consider this here in detail anymore. Well, the opacity strongly depends on chemical composition, because, of course, these bound transitions will depend on which atom we have. Also, the free transitions will depend on which particular atom we have. So if we have a hydrogen atom or if we have an iron atom, this will very much influence these transitions and therefore very much influence the opacity. So keep in mind, opacity strongly depends on chemical composition, and to calculate the opacity, it's again a very hard task for atomic physicists, and there are nice guys who provide tables depending or with parameters, chemical composition, provide for different chemical compositions as a function of temperature and density or pressure and density, provide the values of the opacity. So for realistic calculations, there are nice guys who have provided the opacity tables. There are essentially 3 projects. Well, one of them is sponsored by Los Alamos laboratories. These are the LAOL opacities. The other one are sponsored by Livermore laboratories. These are the Opal opacities. And there is a project, OP project, which is done by MHD, which does not mean magnetohydrodynamics. This is Mihalas, Hammer, and Deppen, three guys who thought they would like to provide opacity tables for their honorary astronomical colleagues. So there are groups which deal only with the calculation of opacity tables. This is a non-military military project. The other ones are somehow connected to military. Of course, you see this with the address Los Alamos and Livermore. Actually, the first opacity data came from experiments with the atomic bombs. So the first hints. So that's why these guys are interested for other reasons also in opacities, and in their free time they calculate opacity for their astronomical colleagues. Okay. So the parameters of these tables usually density, temperature, or alternatively pressure and temperature and chemical composition. Do we have to stop here? Okay, just one result. Okay, so what one gets here is here again the range. Again, this is again a log rho log t diagram. Now different values of the densities and temperatures as compared to the equation of state. And here you see for high temperatures and low density, the dominant source of opacity is the electron scattering. Once we decrease temperature, increase pressure, then we have the photoionization processes, bound-free and bound-bound transitions. There is a small range where we have three free transitions, and at very low densities and very low temperatures and high densities, then we have conduction by degenerate electrons. So for a wide range of parameters, electron scattering and the bound-free and bound-bound transitions are the important sources for opacity. Let me show a next diagram. Well, once we cut through this diagram and plot the opacity as a function of temperature, keeping, for instance, the density constant, we see that the kappa has typically, the opacity has typically 3 maxima, and for high temperatures it goes to value around 0 point something. So the question is, what causes the level here at high temperatures of, say, around a little bit below 1 centimeter squared per gram? High temperatures, everything is ionized. Everything is ionized means also all atoms are ionized. So we cannot have bound-bound or bound-free transitions because all electrons are gone. We just have the nucleus. So what is left, but what is always left if fun? It's which source of opacity is left at very high temperature? Electron scattering. So it levels off at the value of electron scattering, and if we go to moderate or low temperatures, then we observe these 3 peaks. I'm sorry, I have to tell a small story. This dotted line is based on an opacity table which was available until the 1990s. And this shows the 2 peaks here, but it doesn't show that one. And in the 1990s, some clever guys at Los Alamos and Livermore, they have sit down and saw we missed so far a source of opacity, and this source of opacity provides this new peak. And so all stellar evolution calculations essentially had to be redone because this peak was missing so far. And it is also very important for pulsations, because each of this peak can be responsible for for an instability of stars for exciting stellar pulsations. Well, we'll talk about or interpret this diagram tomorrow then. So, but just for thinking about until tomorrow, consider this diagram. We will comment on that tomorrow more. Okay, thanks for the day.